Welcome to Darasa Online. My name is Josia Mwakitalima. I'm a chemist teacher, so I'm here to discuss with you some issues and concepts in chemistry subjects. So you are warmly welcome. And for our discussion today will be on the topic known as selected compounds of metal. And we will consider on the subtopic known as carbonates and hydrogen carbonates. So, from carbonates and the hydrogen carbonates, here we will mainly deal on carbonates. And from our introduction, if you remember, the carbonates and the hydrogen carbonates, they are derivatives of carbonic acid. As we know that carbonic acid have a formula of 2 hydrogens, CO and 3 there. So this is carbonic acid. So when we talk of carbonates and hydrogen carbonates is when the hydrogen atom is replaced by a metal. So once one hydrogen atom is replaced by a metal, then the compound is known as hydrogen carbonates. But if 2 hydrogen atoms are being replaced by a metal, then it is known as carbonates. So here is that, taking an example, when one hydrogen atom is replaced by a metal, then taking an example of sodium. If sodium have replaced one hydrogen to this carbonic acid, then you will have sodium and one hydrogen will remain there, will be sodium hydrogen carbonate. But if both hydrogen atoms are being replaced by sodium, then it will be sodium carbonate. So this is now what we call it carbonates and hydrogen carbonates. And as what I have said here, our concern here is mainly on carbonates. Our concentration here, as what we have said here, is on carbonates. So carbonates can be classified into 2, where we have the soluble carbonates and we have the insoluble carbonates. The soluble carbonates are those carbonates of metal which dissolves into water and form a clear solution. So this one dissolves into water and form a clear solution. Whereby the insoluble carbonates are those carbonates of metal which do not dissolve into water. So this one do not dissolve into water. And the soluble carbonate includes the carbonates of more reactive metals. And when we talk of carbonates of more reactive metals, that means we mention the carbonates of group 1 metals. So here includes the carbonates of more reactive metals. Taking an example here is we have sodium carbonate and the potassium carbonate, and the non-metallic carbonates, which is ammonium carbonate, also is found in this group of soluble carbonates. But for the case of insoluble carbonates are carbonates of less reactive metals. So these ones are carbonates of less reactive metals. And to mention some of them, we have calcium carbonate, we have magnesium carbonate, we have zinc carbonates, and etc. So these are insoluble carbonates. So as what I've said at the beginning, that here we are mainly dealing with many issues, and the main issues that we are going to discuss in carbonates. So issues to be discussed in carbonates is, one, we'll discuss about the action of heat on metal carbonates. We'll also discuss about the non-existence of carbonates of aluminium and the iron 3. And the third issue to discuss will be the reactions of carbonates with the dilute acids. So these are the main issues that we have to consider now in our discussion. So let us now start with the action of heat on carbonates. To mention the carbonates of our selected metals, here we have sodium carbonate, we have calcium carbonate, we have magnesium carbonate, we have copper carbonate, we have lead carbonate, and we have zinc carbonate. Now, the action of heat on this carbonate depends on the packaging of the ions or of the particles that make that carbonate. Now, for the case of action of heat on sodium carbonate, is that sodium carbonate do not decompose on heating. So here, if you have sodium carbonate, then when heated, we say no decomposition takes place. And this habit is for all carbonates of group 1 element with exception to lithium carbonates. So here it means that even potassium carbonate, when heated, does not get decomposed. So no decomposition. So you may ask yourself why this is happening. This is due to relatively large size of sodium and the potassium, which now appear to be the same to the size of carbonates, which makes it to be very strong packaging of the particles within that carbonate. So to heat it, that means they cannot decompose easily. That is what is happening to the carbonates of more reactive metals. But if we come to consider for the carbonates of other metals, so the carbonates of other metals, taking an example of magnesium carbonate, when heated, decomposes into magnesium oxide plus carbon dioxide gas. So it's your task to balance the equation. But also lead carbonate, when heated, decomposes into lead oxide then plus carbon dioxide gas. So if the equation is not balanced, it's your task to balance it. So that is what is happening to carbonates of our selected metals. Now, the degree of decomposition varies from one carbonate to another carbonate. Is what we have said here, that for the case of sodium carbonate, when heated here, no reaction or no decomposition takes place. But for the carbonates of calcium and magnesium get decomposed on strong heating, while the remaining carbonates here get decomposed on mild heating. Then it's also a question you can ask yourself, why these differences? The difference here is that for the carbonates that decompose on mild heating is due to large size of the metal carbonates, of the metals, than the carbonate ions. So here is that this is due to large size of our metal is copper, we have lead and the zinc, than the size of our carbonate ions. So this makes poor packing of the particles within their structure. And the poor packing of the particles within the structure of these carbonates results into decrease in decomposition temperature of the carbonates. That's why on mid heating, then they get decomposed and resulting into carbon dioxide and the metal oxide of our carbonates. Different from what is happening from calcium carbonate and magnesium carbonate. As we know, the enthalpy of formation here for sodium carbonate is very low. That's why it doesn't decompose at all. But for the carbonates of calcium and magnesium get decomposed on strong heating, since the enthalpy of formation is not low like what is happening to sodium carbonate due to their size that differs. That of sodium is different from that of calcium and magnesium. So the packing of the particles in calcium carbonate and magnesium carbonate is not strongest like what is happening to sodium carbonate. That's why it gets decomposed on heating. So that is about the carbonates, or the action of heat on carbonates of selected metals. So of the carbonates mentioned, we have not mentioned about aluminum carbonate. We have not mentioned about iron 3 carbonates. They are also metal. But why don't we mention them? It is now another issue that we need to discuss, which is now the non-existence of carbonates of iron and aluminium. So after a short break, we will be back. So we have the non-existence of aluminium carbonate, and the iron 3 carbonate. If you go to your lab and find the carbonates, you will never find the aluminum carbonate and the iron 3 carbonates. So why now are they not existing? So starting with the aluminum carbonate. Aluminum carbonate does not exist. This is due to the smaller cationic size of aluminium and the high polarizing power of aluminium. The smaller cationic size of aluminium and the higher polarizing power of aluminium polarizes the oxygen carbon in the carbonate and cause or weaken the bond, and hence resulting into breakdown of that oxygen. Then the resulting product becomes the aluminium oxide. So this is due to smaller cationic size of aluminium and the high polarizing power of aluminium, whereby the smaller cationic size and the higher polarizing power results into this one weaken the carbon oxygen bond in carbonate ion. So when it weakens the carbon oxygen bond in carbonate ion, it means that the aluminium now become very exposed to the atmospheric vapor. Thereby now the aluminium now capture the atmospheric vapor and resulting into formation of aluminium hydroxide and the carbon dioxide. So if this is aluminium carbonate now, since aluminium have smaller cationic size and high polarizing power, so it captures the vapor in the atmosphere and breaks down to release aluminium hydroxide and the carbon dioxide gas. So it's your task now. You can balance the equation. So that is why now the carbonates of aluminium does not exist. But if it is in solid state, the aluminium carbonate breaks down, releasing aluminium oxide and the carbon dioxide gas. So under any condition now, due to these reasons, then aluminium carbonate cannot be prepared or does not exist. And if we come and consider about what about the iron-3 carbonate? Iron-3 carbonate is that the iron have smaller cationic size and the high polarizing power. So it get easily exposed to water molecules and attack the lone pair which is present on water molecules, whereby now water molecules act as a ligands and the iron acts as a central metal atom. So the resulting now formation that the iron combining with the water molecules to form a complex compound of hexaaqua iron 3 ions. So this is due to smaller size and the high polarizing power also. So when now iron will combine with the water molecules from the atmosphere and form the complex compound of iron with 6 water molecules as our ligands. So this is hexaaqua iron 3 ions complex compound that will be formed. So instead of being a carbonate, now the iron from carbonate breaks down or are being released and combined with the water molecule to form that complex compound. And the complex compound here, this one ionizes. It ionizes by releasing hydrogen ions and a complex anion. So the hydrogen ion released will now combine with the carbonate ion that was in an carbonate. Since we have iron carbonate, which is this one, so the ion that will be released now will combine with water molecule to form the hexaaqua iron 3 complex ion. And the carbon, after ionization, the hydrogen ions released now will combine with these carbonate ions. And that carbonate ions, which is this one, and form the what we call it carbonic acid. And the carbonic acid formed now here is a weaker acid. And the carbonic acid dissociate. So the carbonic acid dissociate. Carbonic acid, since it's a weak acid, dissociate to release carbon dioxide and water. So the reaction now here, you will never find again what we call it iron carbonate, which means now the overall reaction will now be iron carbonate once being attempted to be prepared will react with the water molecules and form iron hydroxide plus carbon dioxide, then plus water molecule. So it's your task to balance that kind of reaction equation. And for a solid, carbonate of iron. The solid carbonate of iron is hygroscopic. If it is hygroscopic, that means it can absorb the water from the atmosphere. And by absorbing water from the atmosphere, then the reaction will proceed as what we have observed here. That iron now carbonate will absorb water from the atmosphere and form the iron hydroxide, then will be plus carbon dioxide plus water molecule. So whether it is in liquid state or in aqueous state, still the iron carbonate cannot exist. So that's why now we do not have iron carbonate and the aluminium carbonate. From there now, let us go to another concept, which is the reaction of the carbonates with dilute acids. So we have the reactions of carbonates with the dilute acids. Let us start discussing with the action of dilute hydrochloric acid. Here is that all carbonates reacts with the dilute hydrochloric acid and resulting into formation of a solution of their chlorides, carbon dioxide, and water. So here, taking an example of sodium carbonate, when treated with hydrochloric acid, the resulting product will be the sodium chloride plus carbon dioxide and then plus water. But with the exception to only lead carbonate. Lead carbonate reacts with dilute hydrochloric acid and resulting into formation of solid lead chloride. And the solid lead chloride prevents further reaction of the acid to that carbonates. So taking an example as our carbonate, which is lead carbonate, when reacted with hydrochloric acid, the product is lead chloride, then plus carbon dioxide and water. But the lead chloride formed is solid. So which means that this one now prevents the further reaction to take place. So that's why a vessel made up of lead carbonate can be used to transfer the acids. Since if this is our vessel made up of lead carbonate, then when you pour into the HCl, then just a very small amount of HCl will react and form a coating layer. And that coating layer will prevent further reaction. As a result, now an acid can be carried from one point to another point by using lead carbonate. So the reason behind is due to formation of a coating layer of lead chloride. And also we have another reaction of carbonates with dilute acid, which is now with dilute sulfuric acid. With dilute sulfuric acid, all carbonates react with dilute sulfuric acid, resulting into formation of the metal sulfate. But the metal sulfate formed are soluble, but it is only with the exception to the lead carbonate and the calcium carbonate. The lead carbonate and calcium carbonate results into formation of solid sulfates. So all carbonates with the exception to that of lead and the calcium, they react with the dilute hydrosulfuric acid and form their soluble sulfates. Which means that, taking an example of sodium carbonate, when treated with the dilute sulfuric acid, then our product here is sodium sulfate B plus carbon dioxide, then plus water. So these are our products, but the sodium sulfate formed here is an aqueous. So all other metal carbonates, with the exception to that of lead and calcium, results into formation of their soluble sulfate. But for the case of lead and the calcium carbonate, so lead carbonate, when treated with dilute sulfuric acid, they result into formation of lead sulfate, which is solid, then plus carbon dioxide plus water. So to balance is your task now to do, to complete those equations. So lead sulfate formed here is solid. So even calcium carbonate will also result into formation of calcium sulfate, which is solid, then plus carbon dioxide gas, then plus water molecules. So the calcium sulfate formed is also solid. So the solid products formed here prevents further reaction. So now here, that's why the carbonates also of lead and calcium can be used in transportation of sulfuric acid, since they form a protective or coating layer on the surface, so that the surface now prevents further reaction to take place. Now, all these issues that you have discussed are the issues that I analyzed first, that we are going to discuss them. But for a chemical test now, how can you identify that this is carbonate, or a carbonate is present into a certain compound? We have now the chemical test for carbonates. Normally here for soluble carbonates, we use magnesium sulfate. whereby if you have your test tube with a solution of any metal carbonate and you add into it magnesium sulfate, then a white PPT is formed. And that white PPT indicates the presence of carbonate. So a white precipitate is formed. For insoluble carbonates, we use nitric acid. This is nitric acid. Taking an example of insoluble carbonate, which is lead carbonate. So if lead carbonate is treated with the solution of nitric acid, the product here will be lead nitrate then plus carbon dioxide gas and the water as a liquid. So the gas which is now liberated here, which is carbon dioxide gas, when it passed through lime water, the lime water turns into milk color. So turns into milky color. And the milky color that are being observed indicates the presence of carbonates inside the sample that will be given. So that is how you can test the presence of carbonates. For soluble carbonates, then we use magnesium sulfate, whereby the white PPT of magnesium carbonate is being formed. So, for example here, that means if we take an example of sodium carbonate, when reacted with the magnesium sulfate solution, then this is an aqueous and this is also an aqueous. Here, the white PPT will be of magnesium carbonate, which is sold and other products. You can finish it up. So this is what appears as white PPT. For insoluble, then we use nitric acid, where carbon dioxide is liberated, and when it passed through lime water, the lime water turns into milky color. So that is now how you can identify the presence of carbonates into a given compound. So after a short break, you'll be back. Okay, welcome back now to some questions that may involve or may you use our concept that we have discussed in solving them. And the first question is that you have been asked to explain the effects of heat on the carbonates of sodium, magnesium, and zinc. Give a chemical equation in each case. So which means that our carbonates here is that of sodium, magnesium, and zinc. And you have to explain by giving a supportive equation to each carbonates. I know you remember now. Test yourself now that we have sodium carbonate. When heated, then you are asked to give the product or to explain the product that will be formed. We also have magnesium carbonate. When heated, to give the product. And also we have zinc carbonate. When heated, what will be the product? Now tell my dear students, what are the products? Do you get it? I know you remember that sodium carbonate is resistant on heat, so it doesn't get decomposed on heating. So here we say no reactions. The reason behind it, I have told you at the discussion point, so you have to explain it yourself. Then I will leave you a number for any consultation to see if we have explained well what makes sodium carbonate not to get decomposed after heating. But for the case of magnesium carbonate, we said it get decomposed on a strong heating, releasing carbon dioxide, releasing the metal oxide, carbon dioxide, and the carbon dioxide gas. So you can balance the equation. But zinc carbonate get decomposed on mid heating into zinc oxide and the carbon dioxide. Also, if the equation is not balanced, it's your task to balance it. So that is what you are supposed to answer such kind of question, to explain the heat. So before writing the supporting equation, you have to explain what is happening. After explaining, then you give the chemical reaction to show that reaction. Now let us go and consider question number 2. Question number 2 is that what will happen when dilute hydrochloric acid is added to a powdered lead carbonate? Support your argument with a chemical equation. The question is so simple. If you remember our discussion, we said that lead carbonate, when reacted with dilute hydrochloric acid, it leads into formation of lead chloride, which is solid. Then the other product is carbon dioxide and the water. I know you remember this lead chloride formed is very, very tough, or is a coating layer that prevents further reaction. So those are explanations that you have to explain, and then you write the chemical equation that will support that explanations. Now the other questions now will be just an assignment for you. The third question now I will leave to you as an assignment, and after doing it, I will leave my number for any consultation. Question number 3. Now this is your assignment, and it will be the first question as your assignment. And the question is, why aluminium carbonate does not exist? I know you remember when we were discussing the non-existence of aluminium carbonate and iron 3 carbonate. So this is a question now. You can answer it referring to the knowledge that you have discussed. That is now the first question assignment. And the second question for assignment now the second assignment for you is this one, which is question number 4, according to the series of questions that you have tried to answer some of them. So the question is, dilute nitric acid is added to a green solid sample P. A blue solution Q is formed, and a gas R that forms a white precipitate with lime water. The blue solution is evaporated to dryness and then strongly heated in a crucible. A black solid S, brown fumes of gas T, and a gas that lights a glowing splint are formed. Now you are asked to identify the solid P and S, that is Roman 1A. Roman 2A, identify the gas R and T. And part B, support your answer with a chemical equation. How does the solid P react with dilute nitric acid? And the Roman 2, how did the solution S form? So these are the 2 questions for as an assignment for you to do it. And after doing it, you can submit it to me through my phone number, which is 0713 14 09 14. 0713 14 09 14. Now, in overall, these carbonates, how do we use the carbonates? The application of carbonates is that they are used in manufacture of building and construction materials. A good example is calcium carbonate. Calcium carbonate, when powdered, they are used in manufacture of what we call it cement. Not only that, also in medicine industry, we have magnesium carbonate. Is used in treating heartburn. That is an application, but also they are used in agricultural activities as fertilizers. And here mainly is the non-metallic carbonates, which is ammonium carbonate. Ammonium carbonate is used as fertilizer. So these are some of the uses of carbonates. That's why we study them, and they are very vital in other activities that we do use in our homes. Okay, another application of carbonates, we have washing soda. Washing soda, which is sodium carbonate, is used in softening. Hardy water, so and etc. So these are some of the application of carbonates. That's why we study them, which means that you can use them in different activities at your homes or at your workplace or anywhere else. So that is now the end of our discussion today. So see you next lesson. Keep on following us. Thank you very much.